Okay, so this is a follow-up video for you to be able to make what we discussed in the previous video more intuitive. So let's look at the relationships between the various variables that we were describing in the previous video. So in this video, we want to look at magnetic flux, how it's related to your area and the angle. We looked at this in the previous video, but we need to make it more clear. So let's suppose you have in this video, we're going to be focusing on loops, which are coils of a specific area. So these are the ones that we use in our generators or electric motors. So we are going to be focusing on the area of a loop or of a coil. So here we are defining magnetic flux as the amount of magnetic field that is passing through a loop of wire, or rather through, this is just the magnetic field that is passing through a given area. So the given area is the loop of a wire. So let's suppose we have a loop A with a specific area, and when we decrease our area, you can tell by the number of crosses that are passing into the page there. Remember, the crosses in our 3D vector notation are representing the magnetic lines of force that are going into the page. So you can see that for the first area there to my left, there are a larger number of lines, and there are a smaller number of lines to my right. So that means that the magnetic flux is affected by the area. So the larger the area, the larger the magnetic flux. So that is also supported in that equation. There's a linear relationship between your area and your magnetic flux, which is given in Weber's. Let's move on to also see that the next term in the equation there after area is your magnetic flux density. So I have given two regions there. To my left is a larger flux density and a smaller flux density. You can tell by the number of lines, magnetic lines that are passing through that area. Remember, this is per square meter, so which gives us a picture of the strength of your magnetic field. So there's a larger strength there to my left and a smaller magnetic strength to my right. So if I keep my area constant, that would be the flux that passes through that area. And if I keep it constant too and put the same loop into a different field with a smaller flux density, then you can see that the flux or the number of field lines that are passing through that area are going to be smaller when your B factor there or your flux density is small. So I hope that's very clear. And now when it comes to the angle, you have the largest lines passing through a given area when the angle between the normal to the shape that you are given there. The normal line, which is a line that is perpendicular to the face of the shape. So let's show the normal line. So that will be the normal, which is perpendicular to the face of the shape that you are dealing with. If that line is parallel to the field lines, then we have the greatest flux. In other words, the angle between that normal line and the field is going to be 0. So and then you can have your normal line at an angle to the field lines as shown there, and that would, as you see, decrease the flux or the amount of field lines that are able to pass through that shape. So if it's a square, if you tilt it like that, it should be intuitive to you that then the lines that are going to be able to pass through there are going to be fewer. You can count the lines that I've put there. We have 1, 2, 3, 4, 5 lines in total, and you can see for the first diagram there to my left, all the 5 lines are cutting through that shape. But if I tilt it, I know I have only 3 lines that are able to pass through. So that is the idea. And you can have your normal perpendicular to the face of the shape being perfectly perpendicular to the lines of magnetic force, and in that case there is going to be 0 flux. So the cosine of 0 is 1, so you're going to have let's say 100% there of the lines passing through your loop. And in the second instance there, let's say our cos is 45, you can see that it's now 0.7. That would be a decrease from 100% to 70% flux. And cos 90 would be equal to 0. So when it's perpendicular like that, the normal line is perpendicular to the lines of magnetic force, then you are going to have 0 magnetic flux. This is important as you look into the function of generators and motors. So let's look at examples here. So determine the magnetic flux through the square of a wire with that is 35 centimeters long on each side. So you can draw our normal, and we are seeing here the lines of magnetic force are perpendicular, parallel to the normal. So the angle between them is 0. So if we plug in the values there, we have 0.35 meters. You have to convert your centimeters to meters by 0.35, since it's a square, times your magnetic field strength, 2.65 teslas, and plugging in the cos of 0, which is 1, you have 0.32 webers. So let's change the situation. We now have shifted our face such that the magnetic field lines are coming at an angle into the loop, and the normal there, which is perpendicular to the face of the loop, is shown. So the angle between the lines of force, magnetic lines of force, and the normal to the shape, the loop, is now in this case 35 degrees. So we can plug in as before, and cos 35 in this case, if we multiply by this factor, we're going to have 0.27. And if we check, let's check the values here. We're at 0.32 at when our theta was 0, and now we have 0.27. So you can see there's a decrease in the flux due to that angle. So we can have it's perfectly perpendicular to the normal, the lines of force, and when that is the case, you know, cos 90 is 0, so there's going to be absolute 0 flux in that case. So that would be the effect of the angle on magnetic flux. The shape can be a circle, and we still have the same trend. Let's say we have an angle there, and the angle in this case is 55 degrees. So we just plug in our values, and we have to change. We're given the area of the circle there, 75 square centimeters. We have to change it to square meters, which becomes 7.5 times 10 to the power negative 3. Field strength is 5.95 teslas, cos 55. So we get 2.6 times 10 to the power negative 2 webers. So this is how the angle is related. We can also have induced voltage, but we need to understand what is known as Faraday's law. So Faraday's law says a voltage will be induced in the coil when the magnetic flux through the coil changes over time. So there has to be a change in magnetic flux. There has to be a change over time. If there is no change in magnetic flux, if it remains constant, then there won't be any induced voltage. This would be similar to a case where your coil, if you're trying to move a coil into a magnetic field, or a permanent magnet through a coil, this would be similar to where the magnet is stationary or the coil is stationary. So you can look at a simulation here. So this simulation is showing us that if you move the magnet into the coil, then you're going to have your voltage there increasing. So when it's stationary, then there won't be any induced voltage. So there has to be a change in magnetic flux over time for there to be an induced voltage. So there has to be a change over time. When it's stationary, there is no change in flux, hence no induced voltage. So let's look at this. Faraday's law given in symbolic form there is going to be induced voltage is going to your negative number of turns in the coil times your change in area multiplied by your change in magnetic flux density or field strength divided by your change in time. We need to think about the relationships between the variables. So the relationship between induced voltage and area is such that when you increase your area, you're going to increase your induced voltage. We saw that when you increase your area, you increase your magnetic flux. So this would affect your voltage. So there's a linear relationship there. When you change your magnetic strength, field strength, you increase it, you're going to have an increase in the induced voltage. But for time, when you decrease your time, you're going to have a higher induced voltage. What does this mean? It means that when the movement that you're making into and out of a coil is faster, then you're going to have a smaller time, which will increase the voltage. When you are slower, you're going to have a larger amount of time, and that is going to decrease your induced voltage. And to the number of turns, when you increase your number of turns in the coil, then you're going to have an increased voltage. So let's move on to look at examples. So I want to show here that the change in flux is going to affect your induced voltage. So let's suppose here you have a loop with that area, but you begin with a zero magnetic flux. There are no magnetic lines of force that are passing through or cutting through your coil, and you change that over time, and you change it to 75 times 10 to the power negative 3 Teslas. So you started off with 0, and you changed your magnetic field strength there, such that there are now lines of magnetic force cutting through your loop. So let's suppose this change occurs over 3.5 seconds. What does this mean? So what is your induced voltage? There's a change in flux there. So we are going to say our change in area times our change in magnetic field strength over our time. And our n has disappeared there because we are assuming that the number of turns is 1. So n is constant at 1. Otherwise, you would multiply by the number of turns in the coil. So we just want to see what happens here. So the change is actually a change in your magnetic field strength or magnetic flux density. So the area has remained constant. So when we plug in there, our area is 0.4 by 0.4 times our change in magnetic flux density. So we are saying our final minus our initial. So 75 times 10 to the power negative 3 minus 0, our initial, we get our 75 times 10 to the power negative 3. We divide that by the time, we're going to get 3.4 times 10 to the power negative 3 volts. So this would be the induced voltage. Okay, so let's look at a second example where in this case you're going to be changing your area, your magnetic field strength, flux density is going to be constant at 4.0 milli-teslas. So what you're doing, this would be similar to what we were showing. Here you'll be moving your coil, your loop into a magnetic field. So in other words, the area which is exposed to the magnetic field is going to be increasing over time. So let's show that. So if I move my coil into a magnetic field, so the number of magnetic lines that are cutting through my loop is gradually increasing as I move the coil into. So let's say I move to that level, and I now have 6 times 10 to the power negative 4 square meters that are exposed to my magnetic lines of force. What does this imply? Let's say this happens over a time of 3 seconds. This would be similar to what I was doing in the simulation previously. So my induced voltage is going to be my change in flux density over time, which is my change in area times my change in flux density over change in time. So if I plug in the values there, my area is changing to a final value of 6 times 10 to the power negative 4. So this final minus my initial, which is 0, I'm still going to get my 6 times 10 to the power negative 4 times my magnetic field strength over my change in time. So 0 to 3 should be 3 minus 0. I have my 3 seconds, and the induced voltage is minus 8 times 10 to the power negative 7. So let's suppose we change our time. We move the coil into and out of that magnetic field very fast, such that the change is going to happen in 1.5 seconds. What does that imply to our induced voltage? So if I put 1.5 seconds instead of 3 seconds, I can see that my induced voltage is increased to 16 times 10 to the power negative 7 volts. So you're supposed to remember this concept, the relationships between the variables, so that you use these in problem solving.